Hello and namaskar. Welcome back to my channel, guys. In this video, we will be discussing the April 2024 paper, okay, which is an end term paper. So we will be discussing this in this video. And if you haven't subscribed my channel yet, then please subscribe my channel. I am very close to 5,000 subscribers. It will help me a lot. Okay, so let's start the video with the very first question, that is, imagine a data set characterized by two features, the feature 1 and feature 2, demonstrating a perfect negative correlation. Okay, there is a perfect negative correlation. That means that the data sets, the feature 1 and feature 2, are negatively correlated, that if it increases then it will decrease. Okay, when applying k-means clustering with k equals to 3, okay, that is, we will ask to 3 nearest neighbors. What is the most likely arrangement of cluster centers that minimizes the within cluster sum of squares? So basically our error is basically what? Sum of squares errors, okay? And we want the arrangement such that it minimizes the within cluster, okay? So first thing is, the option is the equilateral triangle centered around the mean of the data. So do this, do a rectangle, an equilateral triangle will reduce the data, basically minimize the cluster arrangement. So let's look at the arrangement. Okay, so let's say these red points are our data points. Okay, and this line is basically just a linear separator. Okay, and we know that the data here is negatively correlated. Okay, that is, if it increases, then if feature 1 increases, then feature 2 will decrease. Okay, so the best arrangement, okay, of case will be nothing but around, basically nothing but on the line itself. Okay, so what will be the best arrangement? It is not, it will be nothing but on the line itself. So the points on the line, let's say this k1, k2 and k3. Okay, why it is so optimized? The optimal placement of a cluster center is to position them along the line. Okay, why? This minimizes the distance of each point has to travel to reach to nearest center. Basically, from this point, if we want to reach to this point, this point, this point, this point, these. So from here, the distance will be less because this is a, let's say, a regression line. You can say a regression line. So distance from uh, the points on the line to every point will be minimum. Okay, so that's why this arrangement will be a perfect arrangement here. Got it? So that's why this will be the perfect arrangement, and this will be the correct option. Okay, equilateral triangle is not suitable here. Okay, a triangle with two acute angles and all a right angle triangle, so no triangle. Okay, only the points which are on the line will minimize this error. Now moving to next question, it's saying that consider there are two models filtered on one dimensional data set. Okay, so we have one dimensional data set and we have filtered this. Now there are two models we have. Okay, model 1, which it says basically it is a linear model. Okay, model 1 is a linear model, you can see here, and model 2 is a polynomial model. Okay, the question says if both models are trained on the same one dimensional data set and evaluated on the same test data set. Okay, so what it is saying, it is trained on the same one dimensional data set and evaluated on the same data set, test data set. Both have same training data and test data. Which model is likely to have higher bias and lower variance. Okay, the options are these. So let's understand. So for model 1, that is a linear model, it will have more bias because it is less flexible and may not fit the data well if true relationship is non-linear. Okay, so let's say if our test data is there and in test data our relationship is not linear. Okay, then what will happen? It may not fit the data well correctly. So that's why it will have more bias. Also, it will have lower variance. Okay, because it is simpler and less sensitive to fluctuation in the data point. Okay, basically in training data, it is simple. Basically, it's just a line. Okay, so it is less sensitive to any fluctuation in the data or outliers in the data. Okay, whereas model 2 is a polynomial model which has low bias because it can capture more complex relationship including quadratic patterns also. Okay, that's for that reason it will have low bias. Okay, whereas it will have high variance because it is more complex and can fit the training data more closely. Okay, potentially captures noise as well. So because this is a polynomial type, it will capture, it will go through the data more closely, which means that it can, if there is an outlier, it will be sensitive to it, right? So that's why it will have high variance and low bias. Okay, I hope you understand this. Now, next question. Consider a logistic regression model for binary classification problem with two features x1 and x2. The feature vector is this and the label is this. Okay, level is in 0 and 1. The threshold for inference is 0.5. Okay, the dummy feature and the weight corresponding to it can be ignored for this problem. Let x1 be horizontal axis and x2 be vertical axis. You are given two feature vector, that is x1 which is this and x2 which is this. So we have two feature vector x1 and x in the form of x1 x2. Okay, the weight vectors make an angle theta with positive x-axis, that is horizontal x-axis. Okay, each theta corresponds to a different classifier. For what range of values theta are both x1 and x2 predicted to be class 1? Okay, for what range of value of theta? So basically we have to find the value of theta for which the class is predicted to be 1. There is some hint, that is to draw the weight vector w, plot w and w2 and draw an arrow starting at the origin to this point, and also given that tan 60 is root 3. And these are the options. Okay, so let's look at it. So here what do we want? We want that prediction should be class 1. So when it will be in class 1? When w transpose x will be greater than equals to 0. Okay, z will be 1 when w transpose x will be greater than equals to 0. We have two vectors, this, and let's say this is our point and this is our w. Okay, this is our w, making angle theta as it says with the horizontal x-axis. So this will be your cos theta and this will be your sin theta. Okay, so w is a point, so x component will be cos theta and y component will be sin theta, right? As w makes angle theta. Now, for class to be 1, we know that this condition has to be true. So that means that w transpose, that is this transpose into x. So let's say we take the first vector, so it will be 1 root 3. Okay, first feature is this, that will be greater than equals to 0. From here we will get this when we do the, this is nothing but the dot matrix multiplication. When you do this, you will get something like this. So let's say I marked it as 1. Similarly, for second feature vector, you will get something like this. Okay, I marked it as 2. Now what I did, I just divided cos 1 with cos theta. Okay, so when I divide this with cos theta, okay, so it will be cos theta, it will be cos theta, so it will be 1, and here it will be tan theta, right? So it will be nothing but 1 plus root 3 tan theta greater than equals to 0. That is root 3 tan theta is greater than equals to minus 1. That is this. And for this, basically theta will be 5 pi by 6. Okay. I hope you know trigonometry. Similarly, from second, we will get this minus 1 plus root 3 tan theta greater than equals to 0, from where we will get theta as pi by 6. So our range will be from pi by 6 to 5 pi. 5 pi by 6, that is 30 degree to 150 degree, and this is theta. I hope you got this. Now, next question. Which of the following accurately describe the characteristic function of kernel functions? Okay. First is kernel PCA can reconstruct original PCA if kernel function is this. This is polynomial, right? So our kernel PCA can be reconstructed to original PCA only if kernel function is a linear function, but here it is a polynomial function, so we can't reconstruct our original PCA. Okay. The dimensionality of a transform data set computed using the kernel function is always smaller than the original feature space. So it is not true. As you know, kernel feature basically what it does, it basically projects our data points into higher dimensions to basically capture the linearity in the data set. Okay, so the dimension can be either greater than or equal to, or even it can be infinity. Okay, so that's why this is wrong. Here it says that the dimensionality of the transformed data set computed using kernel function cannot exceed original feature can exceed original feature space. So absolutely this is true. And can be infinity, yes, this is also true. Now next question. Let X in the matrix of this shape D cross N shape and Y be the associated label vector of shape n comma 1. Okay, so basically it is a n rows 1 column, right? This is what it says. Assuming that a linear regression model with loss of sum of a squared error is trained on this data set. Okay, what we did a linear regression model. Okay, in which of these cases the loss on the training data set will be necessarily be 0. Okay, assume that the solution of the model obtained by the normal equation is basically this model. Okay, so the thing is, if y lies in the space spanned of row vectors of x. Okay, this is if this condition is true, then is our data set will be the training error will be 0. So look at here. Saying this means that y can be perfectly represented as the linear combination of these rows vector, right? Because what it says, y lies in the space spanned of row vectors. Okay, so if we are spanning, that means that we can write it in the linear combination, right? So that is what it's saying, which means that there exists a weight w such that x w equals to by exactly, and that is for every point x, the x in x dot w will be exactly equal to by, which is our original data point. So yes, this is true. And if y lies in the space span of row vector of x transpose, so this is not true. This can be possible only if X is a square or full rank matrix. Okay, square matrix. If X is your square matrix, then it is true. That is a possibility is there. Okay. Now next is if all the data points satisfy the equality, this equality, where xi is the ith feature and y equals to 0 for all data points. So if this condition will be true, so let's say that all y values are 0. Okay, all y values are 0, which it's already given. then the sum of features for each data point will be 0. A weight vector w equals to 0, 0, 0, that is a 0 vector, will perfectly satisfy the condition with 0 loss. Correct? So 0 vector, this vector, weight vector, will perfectly satisfy this condition. Right? That is x1 plus x2 plus up to xd. The sum of all these will be equals to 0, and y will be equals to 0. Sorry, I am yawning. Basically, it's 3n. Okay, so that's it. Avoid that. Next, if all the data points satisfy the equality of this, where xi is ith feature and yi is equals to 0. So look at it. It is nothing but a cubic relationship. Okay. So as it is a cubic relationship between the features, it does not guarantee that a linear model can achieve a zero loss because it is a cubic, right? Cubes are like this, correct? Cubic. So it does not guarantee that a linear model can achieve a zero loss on this cubic relationship. Okay, that's why it is not a correct option. Now, next question is, consider the following dataset on which soft margin SVM is applied. So this is a dataset. Okay. So if you remember, so for our support vectors, only those points will contribute, that is either on the support vector or either the misclassified points. That is, let's say in this case here it is a misclassified, it is a misclassified, this is on support vector, this is on misclassified, this is on support vector. So these all which are circled are the points which will contribute to our SVM algorithm. Okay, so here it is saying point A and N are subset of support vectors. Yes, this is AFAN, yes, this is also, and FACIN, yes, this is also. So these all are the subset which will contribute for the optimal W. I hope you have seen my SVM video. Also, I would like to say you that the PDF of this PDF you will get in my Telegram channel. So if you haven't joined my Telegram channel, do join that also. Okay, let's move to next question. Given two-dimensional data set where points from class 1 are these and points from class 0 is these. So we have given all the points, okay, from class 1 and class 2 and saying which is the correct. Okay, and these are some options, that is the given data points from class 1 and 0 can be linearly separated using a hard margin, or a perceptron model and a hard margin can give different decision boundary, and the SVM can do this, or the width of separation will be exactly 4. Okay, so let's first plot the data set. So when we plotted this data set, these all are class 1 and class 0. So we can see that we can linearly separate it, right? We can linearly separate this data set. So yes, it is linearly separable. So we can use hard margin. So our first option is basically correct option. That is, we can separate it using hard margin SVM. The second option is a perceptron model and the hard margin SVM will give different decision boundary. So of course, because in perceptron models, there can be many W, right? Similarly, in SVM, it will give a highest margin decision boundary, right? So yes, both will give different decision boundary. Third, a soft margin SVM would be more robust than a hard margin. So no, as the dataset is linearly separable, uh, hard margin will give zero, can give zero errors, right? Also, next is we don't have info about basically to know that the width of the separation between the two supporting vectors is 4. Okay, so we don't have like optimal W for which it happens or anything like that. So we don't have enough info to comment on this. That's why this option is also incorrect. Now, next question. Consider the following two-dimensional data set. Okay, with two classes, +1 for blue points and -1 for red points. And Adaboost algorithm was run on the dataset using the decision stumps as a weak learner. Okay, and these are the algorithms. When training the new weak learner HT, okay, that is a decision stump at Th iteration, we choose split that minimizes the weighted misclassification error with respect to current DI. Choose HT that minimizes this, that is d of t of 1, h of t not equals to 0. Based on the above data, give the following answer. And the question is to train the second decision stump. Okay, it's not asking about first decision stump, it's asking about second decision stump. Okay, which pair of point will be assigned equal weights to create the training data set. So basically we have to create the training data set. For that, which weights needs to be assigned. So these are the weights given. So let's look at the data set first. Okay, so these are all red points. There is one red point here and these are all blue points. Okay, so let's say if we take a weak learner first. So let's say we take a normal this learner which will separate most of the points, like these points it is correctly separated, these points are misclassified. Okay, so let's look at the first, that is 2 2 and 1 2. So we see that 2 2 is here and 1 2 is here, these two. So do these two will give a equal weight to our training data set? Basically, do it will it give? No, it will won't give according to this split, right? Let's check the second. That is 2 2 1 4. 2 2 is here and 1 4. 1 4 is here. Will it give a correct weight? Yes, it can give, but 1 is already correctly classified, so we won't choose this. Next, 1 1 and 1 4. 1 1 is here, 1 4 is here. It will give a correct equal weight? Yes, it will give a correct weight. Okay, both the point will be as both the points are misclassified and will be assigned equal weights. Okay, next 3 1 and 3 4. 3 1 is here and 3 4 is here, right? So do these points will give a equal weight? Yes, these will give a equal weight and these are correctly classified also, but we will choose this because we want our algorithm to maintain the awareness about the correctness of the data as well, right? That we have already classified some data that is correct. So for that reason, we have to choose this also. It will also provide equal weight as well. Now, next question is, consider a soft margin SVM algorithm for a binary classification problem with a data set of two-dimensional space. The optimization problem for soft margin SVM is formulated as this. Subjected to this constant, we have discussed it so many times, where C is a positive constant. Okay, what C is a positive constant. Let uh, W star epsilon star be the optimal solution and alpha star and beta star be the optimal dual solution for the soft margins. Okay, and it is saying that which of the following statement is true about the soft margin SVM. The first option is, if the ith data point lie on one of the supporting hyperplanes, the alpha star will be equals to 0. So if you remember, if the point is lying on the support hyperplanes, then our alpha belongs to 0 and C. I have discussed it in my recent videos. Okay, when I was summarizing this, right? Then I have stated it clearly that if points are on hyperplane, then alpha belongs to 0 and C. So it can take any value from 0 to C. Second option says if ith data lies on the correct supporting hyperplane, okay, it does not pay any bribe. What it's saying, that if ith point lies on the correct supporting hyperplane, okay, so as it is correctly as it the point is correct, we don't need to correct it, right? But why we give bribe actually to basically correct, right? that if the data is misclassified, let's say it has to be here, but it is here. So we give the bribe to come to here, right? But it is already classified correctly, so we won't give any bribe. Okay, so this is a true. A smaller value of C allows for a large margin, potentially leading to less misclassification of training data. No, small c means less emphasis on fitting training data perfectly. Okay, so that's why it is a wrong choice. For a dataset with n points, there will be 2n constant for soft margin SVM. So yes, we have seen that for a single data point, there are two constants. So for n data points, there will be 2n constant. And as C approaches to infinity, the soft margin equals to hard margin. I have already discussed in my video that yes, if C approaches to infinity, it means that bribe is extremely high. That means that it is nothing but a high hard margin SVM. Now next question is, consider a dataset X in R cube. The dataset consists of 4 samples with 3 features. The covariance matrix C of the dataset has 3 non-zero eigenvalues which will follow the linear equation these. Determine the variance. So what we have to find? We have to find the variance. So for variance, if you remember, for finding the variance, basically the sum of all eigenvalues is nothing but equals to total variance. Okay, so from here we will solve these for lambda 1, lambda 2, lambda 3 that are our eigenvalues. Now the variance will be nothing but lambda 1 plus lambda 2 plus lambda 3, that is 6. Okay, so this is the formulation. Next question is, consider a dataset with n observation x1, x2, xn, where each xi is a Bernoulli distribution with parameter p. Okay, for 1 to n. However, you will have a reason to believe that the parameter p might differ for two groups within the dataset. You suspect that there are two groups in the dataset, each with its own parameter p1 and p2. Now develop an algorithm to estimate the parameter p1 and p2 using the maximum likelihood estimation. Apply your algorithm to a dataset with the following observation corresponding group labels, that is this dataset for the group 1 and group 2 respectively. So let's calculate. So we know that for a Bernoulli distribution, the ML estimation is nothing but P equals to summation of xi upon n. This we have done so many times in our stats course, in our MLF course, right? So now it should be remembered, right? So this we already know. So for group 1, we have this data set. So simply we will put it here. So P1 equals to nothing but 0 plus 1 plus 1 plus 0 plus 1 upon 5. That is sum of all xi upon 5, that is 0.60. Similarly, for group 2, we will calculate this is also 3 by 5, that is 0.60. So for both the cases, MLA is nothing but 0.60. That will be our answer. That is a maximum likelihood for P1 and rounded to 0.2. So P1 is this. So this is our 0.6. Next question is, consider the following decision tree for a classification problem in which all the data points are constrained to lie in a unit square in the first quadrant. That is this. If a point is picked uniformly at random unit, okay, then what is the probability that the decision tree predicts this point and as belongs to class 1? Okay, so we need the probability for the point to be belong to class 1. Okay, so I guess there is something wrong here. So just a second. So basically, what happened here is this. Oops. Okay, no problem. Yes, now it works. What is happening? Okay, let's look like this. Okay, so consider the decision tree. Okay, so we have to consider the decision tree. So decision tree says x1 will be less than 0.5, then it will be a no and the prediction will be 1. And if it is a yes, then we have again a question, that is x2 is greater than 0.5, then if no, it is 1. If yes, then it is 0. So for this, our diagram will look like this. Okay, our diagram will look like this, where you can see when we have x1 is less than 0.5. Okay, uh, if it is no, okay, it is no, then it will be 1, that is colored with red. Okay, if it is, then again we check the condition that x2 is greater than 0.5. It is already no, so we see that x2 is greater than 0.5, then it will be yes. Okay, if not, then it will be no, so I just colored the red area. Okay, and for 0 I colored the green area, so you can see the area 1 and area 2. Okay, now we have to find the probabilities. So for probability for area 1, I have written the area 1. So all this red is basically my area 1 and this green is my area 2. Okay, so the probability of area 1 is nothing but you can see there are two rectangles, because it has said that in unit box, right? So unit box means 1 to 1. Okay, from 1 to 0 to 1, and in x2 also 0 to 1. So area will be 0.5 into 0.5 for this small rectangle, basically a square, and there is one rectangle for which 0.5 into 1, that is 0.75. Okay, 0.75. And similarly for area 2, it is 0.5 into 0.5, that is this small area, that is 0.25. Now total area we know that it will be 1, correct? This area plus this area. Now now we want to get the probability of class 1. Class 1, that is this red amount. So it is nothing but the area of class 1 upon total area, that is 0.75 upon 1, that is 0.75. That is our answer. Next question. Consider the following dataset with 6 samples and assume that the features are conditionally independent given level y. Suppose that the test data is this. What is the probability of P of y equals to 0 given x test? Okay, so P of y equals to 0 given x test is nothing but P of x test given y equals to 0 into P of y equals to 0 upon P of x test, right? So we have to find this first, because this is conditional class independence. We already have conditional class independence. Okay, I hope you have you remember this this type of these theories which we have already discussed. Okay, so we have to find this probability of this. So the probability of this will be, first is 0, so we will write 1 minus probability of y equals to 0 coming from class 1. If you know how to read this, let me write it. P of 1 0 is basically probability of coming from class 0 uh, class 1 having y equals to 0. Okay, so for 0 we will write 1 minus this. Here it is 1, so we will write probability of class 2 given y equals to 0, and for this it is again 0, so we will write 1 minus p of 0 3. Okay, now so this is basically probability of y equals to 0 coming from class 1. So let's say y is 0, where y is 0, here in these 3 we have y equals to 0, so we have to check for the class 1. So out of 3 records we can see that 2 records are having 1, so the probability of this will be 2 by 3, and we have to minus 1 by 3 it with 1. Okay, so this will be the value of this. Then we have to find the probability of p equals to, p coming from class 2 given y equals to 0. So y equals to 0, we have 2 ones here, so it will also 2 by 3, which we have written here. Now p of class 3 given y equals to 0, so we can see that all are 1. that is it will be 1, and 1 minus 1 will be 0. So the probability of this will be 0, and if the probability of this will be 0, then this will be 0, then whole this will be 0. So this is the prediction. Next question. Consider a linearly separable binary classification dataset with 1000 points and 100 features. Okay. Assume that there exists a W such that W equals to 1, yi into W transpose xi is greater than 0.5. Also assume that x2 norm is less than equals to 2. And the question is, what is the maximum number of mistakes that perceptron algorithm can perform? So you remember, if you remember, the number of mistakes is basically r upon gamma square, r square upon gamma square, that is r upon gamma the whole square. We also know that r is max of xi norm, and gamma is basically minimum of yi into w transpose xi upon norm of w. So we have already given this. From here we will get r equals to 2 because we want maximum of this, that is this. So r will be 2. And from here we have minimum of this. So minimum of this and we have already given that this is equals to 1. So minimum of this will be, we have given this, so minimum will be 0.5. So we got this. The number of mistake will be this, that is square of this, that is equals to 60. Correct. Next question is, consider a single iteration Adaboost algorithm that was run on the 3 sample points starting with uniform weight on the sample points. The label are +1 or -1 in the given table. Some values have been omitted. Okay. Now we have to find the value of weight of x2, as this is the updated weight. So if you remember what we do, we basically find the weights and then we normalize it to basically get the 1. Correct, if you remember that. So these all are the updated weights. So one way of solving this, we can do that. Sum of all should be equals to 1. So from there we can find this, and it will be basically 1 by 4. Correct? I guess yes, it will be 1 by 4. But I want to basically give you a revision that if we come across this type of problem, how we will solve it. And the way of solving it is basically initial weight. That is what we take. We initialize a weight, that is a uniform distribution, and then we change the weights in the iterative fashion, right? So the first initialization of weight will be 1 upon n, that is a uniform distribution, that is 1 upon 3, because we have 3 data points, x1, x2, x3. Okay. So as we want to find the x2 weight of x2, so weight of x2 is classified correctly. Okay, you can see that the truth level is this and predicted level is also this. So it is classified correctly. So if the weight is classified correctly, then what we do, we basically decreases. We decreases it, right? D will be decreases, that is distribution will be decreases. Okay. So here Wt of +1 is nothing but Wt into E of alpha t, right? And Wt is basically 1 by 3 and E equals to minus alpha t, right? Minus alpha t. Now if you see, this term is basically less than equals to 1, right? This whole term will be then less, it is less than equals to 1, and this is 1 by 3, so it will be less. Also we can see that this is the updated weight of x1, and this x1 is basically greater than this. Okay, because this is less and 1 by 3 is already less. So 1 by 2 is greater than, that is the weight of x1 is already greater than this, which means that which is larger than the initial weight 1 by 3, right? It is larger than initial weight 1 by 3. So from this information, what we can do, that we know that all the weights sum to 1. So and this is already updated weight. Okay, so what we do, we will then combine it and will be say it will be, the sum will be equals to 1. From there we can find this. Okay, but the main issue, way of solving this is basically from here. Now here alpha t is basically the activation function, right? And if we have given the activation function, then we can find the iterate basically updated parameter. Okay, so if we are given, let's say, activation function, and we know the initial parameter, right? in initial distribution. So we know how to basically calculate those weights. Okay. So yes, one more question that is from neural network. Consider a simple neural network with one hidden layer. Okay, one hidden layer architecture. Input layer with 3 neurons, hidden layer with 2 neurons, and use a sigmoid activation function. Okay, output layer with 1 neuron using the linear activation function. Now the weight of the weight and biases are given. So in hidden layer, neuron 1 has these weights with this bias. Neuron 2 has these weights and this bias, and for output layer the weights are these and bias is this, and assume that we have this input. So let's create a neural network. Okay, and one hidden layer is there and there is one output layer. Okay, according to it. Now input we have these, so we will fill this values. Now for neuron 1, what it will do, it will capture all inputs, right? It will get the all uh, uh, decisions from nodes, right? All nodes. So from this we will get all the decision to this, and for it w's basically are 0.5, 0, minus 0.2 and 0.8, right? And we have to find the basically calculate the output of neuron 1. Okay, so what will be the output here? So output, we know that for every neuron the output is basically nothing but the linear combinations, right? So it will be nothing but w1 x1 plus w2 x2, basically w2 times this, w1 times this plus w times this, w3 times this, plus the bias b. Okay, because we are introducing the bias, so plus bias will be there. That is, we come up with 0.98, right? Now for output layer, it is nothing but alpha times this. Okay, that is basically output of neuron 1 we want. So basically we want the output of this. So for this we will have alpha times this, alpha time whatever it comes, right? Basically alpha times the linear combination of all these z, right? So basically activation function of this. So activation function is a sigmoid, as already mentioned in the question. So and we know that sigmoid function this, and z we have already found, that is this. So we put the value of z and it will come as 0.7272. Okay, so our sigma 1 will be closely 0.7272. That is basically the output of neuron 1. Okay, similarly we can find the output for neuron 2, that what it will output, right? So we can similarly find the z2, and then again we can put it in sigmoid function and we will get the output of this. So this was the pretty much it, guys. I hope you like the videos, and I don't know if I will make one more paper or not, so please don't comment like please make a paper, because I also have 4 subjects, so I also have to study. So if you haven't subscribed, then please subscribe. Do join the Telegram channel for the PDF, and I see you next time. Best of luck for the exam.